Hello, students. This is Mr. Golumbos, Mr. G, and today we are going to be talking about magnetic fields and what are magnetic fields. So, your warm up today is how do you think a magnet can cause something to move, and what are the different ways a magnet can move an object? Um, so, our question today is why do magnets move objects in different ways? A force, remember, is a push or a pull in an object. Take a second. If you ever see this vocabulary sign and you want to write it down, go ahead and write it down. Contact forces are a push or a pull on an object when two objects are touching. This is friction, normal force, air resistance, spring force, tension force, applied force. We learned about some of these in the last unit. This is an example of a physical force, an RKO. This man is slamming this guy into the ground. That is a physical force, an applied physical force. Distance forces are a push or a pull when two objects are not touching. This is gravitational force, magnetic force, and electrical force. We've learned about gravitational force, but we haven't learned about magnetic forces yet. This is an example of a gravitational force. A apple is falling on this girl's head and it's bouncing off. That is gravity. They are not touching, but there's still a force acting on the apple. So the key concept here, you can write this down in your notes. A magnetic force can attract or repel an object at a distance. Attract means to pull objects toward one another. Repel means to push objects away from one another. So my question is, how can you tell whether two magnets will attract each other, repel each other, or both? This is a bar magnet. The red end is the North Pole, and the other end is the South Pole. You may have played with magnets before. They're really fun. A magnetic pole is one of the two opposite ends of a magnet. So now I'm going to open my simulation. This is on Amplify. So if I go to Amplify, I can open the magnetic field simulation. If you want to play around with it, you can. And let's test that out. So here I have magnets of two of the same sizes, and they have similar poles. I want you to predict, since the North Pole is here and the North Pole is here, the South Pole is here, the South Pole is here, if these objects are going to attract or repel. So now I'm going to hit run now that you've made that prediction. And we're going to see that these two objects, these two magnets, actually repel away from one another. So let's go back to our presentation. A variable is something that can be changed or may be measured in an experiment. So in this experiment, what if I rotate this magnet? So the South Pole is closer to the North Pole on this magnet, and the South Pole here is closer to the North Pole on this magnet. Take a second to predict what will happen. Okay, thank you for predicting that. Let's see what happens. These objects, as you can see, will be attracted to one another. How cool is that? So, the key concept that I want you to know, in a system of magnets, there is a repelling force between like poles and an attracting force between opposite poles. Like poles repel, opposite poles attract. So our next question is, how do magnets work? Magnetism is a force caused by the movement of electric charges. This is a periodic table. We have looked at this in 7th grade. when we learned about atoms and the elements. Each of these elements are part of the periodic table, and they're each made of atoms. Atoms have a nucleus with protons and neutrons, and their shells. There are a bunch of these electrons spinning around the nucleus. The electrons move around the atom. Electric charges that makes the electric charges moving around the atom. Remember, electrons are negatively charged particles. So when they are moving, they are causing the electric charges to move. This causes magnetism to happen. So in a magnet, electrons are moving around the atom. This E symbol is a symbol for an electron, and it's negatively charged, which is that little negative sign. Electrons are moving around the atom. They are moving north to south pole. In that direction, they are moving north to south pole, which causes magnetism to happen. So the Earth is spinning. It's rotating really fast. The core of the Earth, shown here, is made out of nickel and iron. Electrons are moving around the core in unison because all of this nickel and iron, these elements, are moving. This causes electric charges to move, and that causes magnetism to happen. So the Earth is a big magnet. The Earth is spinning. The core of the Earth is made out of nickel and iron. The electrons move around the core in unison. The electric charges are moving, and magnetism is happening. The Earth is a giant magnet. So the key concept, remember our key concept, like poles repel, opposite poles attract. So we have a compass. A compass it's a very itty bitty magnet, and it has a north and a south pole. A compass is a little magnet, opposites attract. The south pole of the needle points toward the north pole of the Earth, and the compass gives you directions. The south pole of this itty bitty magnet will always point to the north pole of the Earth, giving you a sense of direction. So, are all objects magnetic? What about this water bottle? Is this water bottle magnetic? Or this pen? Is this pen magnetic? Let's see in the simulation. So we're going to return back to the simulation. I'm going to take out one of these magnets, and I have aluminum, iron, and wood down here. So I'm going to put aluminum right next to here. And let's make a prediction. Let's predict real quick. Do you think aluminum is magnetic? When I run the simulation, nothing happened. So we have learned that even though aluminum is next to this magnet, it's not magnetic. What about iron? If I put this iron next to the magnet, is it magnetic? Make your predictions now. The magnet moved closer to the iron rod, so iron is indeed magnetic. What about wood? If I place wood next to the magnet, will it be magnetic? No, it is not magnetic. Wood is not magnetic. So let's return to the presentation. So remember, a variable can be changed or be measured in an experiment. So the variable in that experiment was the type of material. I replaced the material with iron, aluminum, and wood. So in our periodic table, I'm showing you which elements are magnetic. Iron, cobalt, and nickel, and GD are all magnetic elements. But not all elements are magnetic. The key concept here to know, iron, cobalt, and nickel are magnetic elements on the periodic table. So this is the core of the Earth. What if I replace the core of the Earth with wood? A block of wood. The Earth is spinning. The core of the Earth is made of wood. Electrons do not move around the core in unison because it is wood. The electric charges are not moving, and magnetism does not happen. What about copper? Copper is not nickel, iron, or cobalt. It's copper. The core of the Earth is made out of copper. Electrons do not move around the core in unison. Electric charges are not moving, so magnetism does not happen. So, let's go back to our question. How can you tell whether two magnets will attract each other, repel each other, or both? We're now going to learn about magnetic fields. Magnetic fields are the space around a magnet in which magnetic forces can act on objects. So it's the space around an object, around a magnet, where there's a push or a pull on an object. Magnetic field lines, a line that connects the opposite magnet poles and represents the strength and direction of the magnetic field. A magnetic field line represents the strength and direction of a magnetic field. These are magnetic field lines. Remember, they point north to south. So let's go back to our simulation and let's see what happens. I'm going to click this little button up here for field lines, and you can see that there are now lines around it. With these two objects, we can see that there's a north and south pole, and these lines do not overlap. They do not align or overlap. Let's make your prediction if these objects will repel or if they will attract. These two objects repel, and you can see these magnetic lines get away from each other. So now what happens if I rotate this magnet? Remember, a variable is something we can change or measure in an experiment. In this experiment, the variable was the rotation of the magnet. I rotated the magnet, and now we see that our magnetic field lines have changed. They are no longer, they now align over one another. So make your prediction. Do you think these magnets are going to repel or attract? When I run the simulation, we can see that these objects attracted. I can even move them further away from one another. And we can see that these objects attracted to one another. So the variable I changed was the rotation of the magnet. And we can see that in a normal magnet, the electrons are moving north to south in this circular motion. When magnets are between unlike poles or opposites, they attract. So these magnetic field lines are overlapping, and so they attract. These magnetic field lines that do not overlap, repel. These are between between similar poles, so they repel. The key concept here, magnetic field lines align around attracting magnets, opposite poles. Magnetic field lines do not align repulsive magnets, similar poles. So what happens when magnets are misaligned? Here we have a diagram of two aligned magnets. And here we have a diagram of two misaligned magnets. Notice that some magnetic field lines do not overlap. Some magnetic field lines do overlap. Let's make a prediction. So when I misalign these magnets, do you think claim 1, claim 2, or claim 3 is true? The magnets will repel, the magnets will attract, or the magnets will both attract and repel. Let's go to our simulation. So I'm going to put two magnets that are aligned, and I'm going to just barely misalign them. You'll notice again, some magnetic field lines are not overlapping. Some magnetic field lines are overlapping. Let's run the simulation. Woo! It does that cool little thing. Squiggles around like that. Let's go back to the slideshow. In that simulation, you saw that attractive and repulsive forces will act on misaligned magnets. So when I run the simulation, they originally will repel from one another, and then they'll attract to one another. Let's move them a little bit further away. They originally repel from one another, and then they attract to one another. So attractive and repulsive forces will act on misaligned magnets. These are test questions to review what we have learned in this video. These test questions will be on your exam at the end of the unit. So if you think to yourself, Mr. Galambos, if I learn these test questions, I will do well on the exam. If I pay attention in this video, I will do well in the exam at the end of the unit. So I put two train cars on the track. What will happen next? The South Poles, there's two South Poles and there's two North Poles. What will happen next? I have two sets of magnets. What will happen to each set? Set 1, the magnetic field lines do not overlap. Set 2, the magnetic field lines do overlap. I place two magnets down like this. What will happen next? We have two North Poles close to each other. I put two train cars on the track. What will happen next? There's two North Poles right here. I have two sets of magnets. What will happen to each set? One, the magnetic field lines are aligning, and in the other, the magnetic field lines do not align. I have two magnetic toys. What will happen next? I have two North Poles right here. That's the end of the video. Very good job. You have learned all about magnetic fields. Great job.